Greetings from the Department of ECE. In this video, we'll be learning about design rules. First, we'll learn why should we follow design rules, and we'll see a glimpse of Lambda-based design rules and the rules associated with it. First, why should we follow design rules? If you want a good product to be obtained after fab, then you have to follow the design rules. So, what the design rules has to do with the performance of the product? So now you're designing a circuit. You're done with the front end part. You have designed, you have simulated, and you have tested. You have tested its function and timing. Functional verification is over. Timing verification is over. Now you are yet to do with your layout backend process. Okay. So obtaining a proper layout and proper routing only will result in achieving the main parameters of any VLSI application. Say power, area, and delay. If you want a minimum area, proper layout is needed. If you want a minimum power, minimum delay, proper routing is needed. If you don't do proper routing, parasitics will be there. Parasitics will cause more delay. Okay, so they are interconnected. Everything is interdependent. So if you want a proper layout, follow the design rules. Okay, design rules will always will safeguard you from moving into parasitics, resulting in parasitics. Okay, when you follow the minimum, that is, it will avoid moving into the danger zone of uh, uh, resulting in short between the layers, shorting of layers, different layers, IC layers, and the breaks in the layers. Okay, you have many metal layers above. Okay, one above one another. Okay, so if those metal layers are not placed with the minimum spacing in between, then you will have more shorts. Okay, likewise, you have many other examples. So if you want a good layout to be obtained, follow the design rules. Likewise, I have mentioned lateral diffusion, dust and rough surface. Whenever you do the fab, you cannot always get a smoother surface. You get a rough surface. So that is obtained one of the costs. Okay, so one of the costs of rough surface and lateral diffusion may be it may not be a proper layout. The circuit may not be designed with a proper layout. Okay, so you will have lateral diffusion. Lateral diffusion is if you have designed, if you have theoretically designed the source and drain to be so and so, its depth should be so and so, it will not be the same. You will have extension of source and drain to some other regions. That will cause again further parasitics, some degradation in your operation or different operation will happen. Okay, so if you follow the design rules, majority of these issues can be sorted out. And lambda based design rules, you have more number of design rules available now. What we are studying in our syllabus is lambda based design rules, and we are not moving deep into it. We are just seeing very few, that is 30% of lambda based design rules I have given here. Okay, so there are n number of rules that are to be followed, and everything is automated now. Okay, so these lambda based design rules, they are scalable. They are not mentioned, or they are not measurable by some unit. Okay, so they are mentioned in terms of a parameter called lambda. They are developed by Mead and Conway, and they are not used for any commercial purpose. It is for academic purpose. Okay, micron rule is only used in commercial purpose or in industry. Okay, so this lambda based design rule, it is scalable. அப்படின்னா என்னன்னா, lambda is nothing but channel length by 2. Okay, so channel length is known to you. So if I change the technology, I can implement the same lambda rules. Okay, so that is why it is called as scalable with respect to feature size. Feature size அப்படின்னா உங்களோட channel length na feature size. Suppose I am designing a system with 180 nanometer technology. What is my lambda? 180 nanometer by 2. Okay, suppose that is 90 nanometer. Suppose I am designing by 90 nanometer technology, my lambda will be 45 nanometer. Okay, so what does it specify? Any design rule. So every your MOSFET in fab, you have learned that it is a layer wise process. Okay, it consists of many layers. Every IC consists of many layers. Each and every layer will be represented with the help of a rectangular block, either with color or without color. Monochrome coding will be used. Okay, in case of layout representation, it is represented, every layer will be represented using a rectangular block. So here when you see, you have minimum width of every rectangular block, minimum width of every layer, or and minimum spacing to be maintained between each and every layer, or between the similar layers, and maximum overlap that is possible, possibly that can happen over two different layers. Okay, how much it can overlap. So all these dimensions we'll be learning in terms of lambda. Likewise, just like fabrication, so for designing CMOS, you had N-well and P-well process, twin-tub process. So here also you have process-based design rules. Okay, for a single CMOS to be fabricated, you had N-well process, P-well process, SOI twin-tub. Like this, here also for the design rules. You have a set of design rules for uh, process based, okay, process specific set of rules, and this is your basic CMOS circuitry. That is, basic CMOS circuit is nothing but inverter. Okay, so here you don't refer anything like a source, drain, gate, substrate, body contact, no, nothing of that sort. You mention everything with respect to layer. Okay, so your source and drain will always be called as diffusion or active area. N plus diffusion, or N plus diffusion is nothing but N type source or drain. P plus diffusion is nothing but P type source or drain. And your gate is nothing but polysilicon, specified by your material. And every electrical contact or connection will be called as contact. Okay, and your substrate or body will be called as, if it is N well, it will be called as well layer. Okay, if it is a twin tub, it will be called as tub. Okay, and everything that you see in a conventional MOSFET, all the terminals, okay, it will be mentioned as in layers. It will be called by its layer. Fine. And now we'll be starting to see the minimum spacing, minimum width. Okay, the minimum width of polysilicon and diffusion line has to be 2 lambda, any diffusion line. Okay, be it N diffusion or P diffusion. Okay. And minimum width of the metal one line has to be 3 lambda. Okay, minimum spacing between the two metal one lines has to be 3 lambda. Okay, so minimum width of poly has to be 2 lambda. Minimum width of diffusion, say P diffusion or N diffusion. Here you have mentioned N diffusion. Okay, so with the help of color, I'm telling you, green means N diffusion, N type source or drain. Metal one will be always represented using a blue color, and poly by red. Okay, this will be will be seeing in stick diagram and layout, all the color codes. And poly to poly space has to be 2 lambda. Metal to metal minimum space has to be 2 lambda. Diffusion to diffusion space has to be 3 lambda. Okay, if you overlap, you have parasitic current or parasitic circuit being formed. Parasitic diode, parasitic BJT, all those will be formed if you place it less than 2 or 3, whatever is mentioned. Okay, as you can see in the diagram, the minimum space between poly to poly, red and red line, is 2 lambda. Minimum space between two anti-fusion lines, 3 lambda. Minimum space between two metal one lines, 2 lambda. And diffusion to polysilicon, you have to have a minimum gap of lambda. And metal lines can pass over both diffusion and poly without an electrical effect. Okay, the reason is, when you learn in stick diagram, you'll understand that why it is possible. That is, your metals can pass over your diffusion, but your gates, okay, your gate, that is polysilicon and diffusion, it cannot pass with an electrical effect. Okay, and you have to leave a space of lambda between a metal and a polysilicon or diffusion. Okay, to show that it is not connected, but actually when you cross and when you intersect poly and diffusion, it is a transistor. Okay, so apart from transistor connections, you have to always leave a minimum space of lambda. Metal connects to polysilicon diffusion by contact. Okay, and contact cut. This is the contact cut, black square circled by your metal. Okay, so this area, okay, contact area has to be 2 lambda cross 2 lambda. The squared area என்னவா இருக்கும் 2 lambda cross 2 lambda. Fine. So this is your spacing and other details. Okay. Here this is my poly, blue is my metal, and pink is my diffusion. So between this contact cut and poly, minimum of 2 lambda is maintained. Okay, and this whole distance has to be 4 lambda. Between two contact cuts, I have to leave a space of 2 lambda. Now the transistor for this the basic transistor layout representation of basic transistor, minimum rules has to be followed. Okay, so with help of monochrome coding, I have explained. So minimum size of transistors. Okay, so whenever a poly crosses diffusion, okay, so you can see this coding. Whenever a poly crosses diffusion, poly is in vertical mode, diffusion is in horizontal mode. When these two cross each other, it forms the NMOS transistor. Okay, whenever p diffusion crosses a poly, then it is called as PMOS. Okay, and if you see this square, that is intersecting square, it has to be 2 lambda cross 2 lambda, and this length has to be 2 lambda, this length has to be 2 lambda, this length also has to be 2 lambda, this length also has to be 2 lambda. So this minimum size of a transistor is mentioned here. Likewise, whenever you measure an implant, this implant, the area has to be 6 lambda cross 6 lambda minimum. Okay. In this slide, we will see extensions and separation. So how far a layer can extend, how far it has to be separated, that is minimum spacing, and how far minimum it has to be extended. So this part we have already seen in the last slide. That is, whenever you form a transistor, minimum 2 lambda, okay, has to be there. So if you see here, diffusion is not to decrease in width below 2 lambda from polysilicon. So whenever you cross a diffusion and poly, you form a transistor. Okay, so diffusion should not decrease below 2 lambda, minimum 2 lambda இங்க இருக்கணும், அப்பதான் அது வந்து ஒரு transistor. அதே மாதிரி இந்த side பார்த்தீங்கன்னா here also minimum 2 lambda has to be there. Okay, wherever you see minimum 2 lambda has to be there. That is why it is minimum size of transistor is 2 lambda cross 2 lambda. அந்த நடுவில் இருக்கிற ஸ்கொயரும் 2 lambda cross 2 lambda இருக்கணும். Extensions also should be minimum 2 lambda. And here if you see this first part we have seen already, that is ஒரு contact கட்டுக்கும் the transistor you must have 2 lambda minimum spacing, and implant and transistor must also have 2 lambda in between. One more thing you must remember, for an implant it has to be a 6 lambda cross 6 lambda. And we'll see for contacts. Okay, so metal 1 to polysilicon or to diffusion. So metal 1 3 lambda minimum width. Okay, this distance has to be 3 lambda. And via is nothing but connection. If you want to connect between two different layers, okay, then you go for a via. Okay, from two different metal layers or two different layers, okay, then you go for a via contact. Okay, here you have specified the minimum width as well as minimum spacing between the contacts. Then the contacts நடுவுல 2 lambda இருக்கு. Okay, and the extension from this one contact, okay, this also has to be 2 lambda. Okay, so and this extension 2 lambda plus 2 lambda cut centered. Okay, so all these has minimum extensions that has to be minimum value, that's minimum length that has to be maintained. Okay, likewise whenever I go for a via connection, okay, so this is how I do a via connection. The distance between this black square and this black square, okay, that has to be 2 lambda minimum separation. And similarly, just like here I have 4 lambda cross 4 lambda for overlap area. Okay, so always remember this box alone will be 2 lambda cross 2 lambda. இது மொத்தமா உங்களுக்கு வந்து 4 lambda வரும். Okay, that is this இந்த இடத்துல ஒரு minimum distance இருக்குல்ல, here you have this as 2 cross 2, இது வந்து ஒரு lambda, okay, and here I have totally 3 and this extended one as 1 more lambda. So likewise I have to design. So you might wonder how to follow such minute rules. All these are automated. Okay, all these are automated. So once you design the front end part, when you go for back end, once you design the once you are done with the layout connections, that is once you map your layout, okay, so connections once you do, when you check design rule, when you give design rule check, all these design rules will be already there. Okay, when you check whatever it is not satisfied, it will give you an error. You can just go over it. And right now we are in more advanced stage. Okay, so everything sorting out and as well as checking as well as sorting out is also automated. Okay, so try to understand that from this slide you can try to understand that you have some design rules to be followed for better product to be obtained. Okay, and you have such kind of lambda design rules for economic purpose and micron rule for industry purpose. So that's all about your design rules. Greetings from the Department of ECE. In this video, we'll be learning about stick diagram and layout. First, we'll learn what is the purpose of stick diagram, and then we'll move towards the color code that is followed for drawing a stick diagram as well as layout for two different processes, that is NMOS process and CMOS process. We'll see what are the steps and rules to be followed again. Then we'll move towards drawing a stick diagram for basic CMOS inverter and one logic gate, that is NOR. Why stick diagram? So before that, what is stick diagram? So it is nothing but a rough pictorial representation of layout. So it is nothing, it stands as a bridge between the circuit engineer and the layout engineer. Suppose you are done with a circuit design, you have completed designing your circuit, you have completed your functional verification, timing verification, the front end part is over. Now you are supposed to create the layout of the entire system which you have designed. Before moving into the layout process, I am going to do a rough draft of layout. That is nothing but stick diagram. Okay, it is a symbolic representation of the interconnections between the components, least components, say transistor. Okay, all the interconnections or the connections between the components of the circuit you have designed or the system you have designed. Okay, and here I am not considering any design rules, any NMOS design rules, CMOS design rules. No design rules comes into picture for stick diagram. It is just a rough draft of interconnections of the circuits, and it is just a rough diagram which represents the layers that is present using color sticks. Okay, so why should I go for stick diagram? In VLSI, one of the main parameter or main performance parameter that is considered is area, power and delay. Okay, so it has to be area has to be minimum, delay has to be minimum, power has to be minimum, and speed has to be more, or else delay has to be minimum. So இந்த மூணு parameter வந்து ரொம்ப முக்கியம். In any VLSI application, these three parameters has to be achieved: minimum area, minimum delay, and minimum power. So what it has to do with the layout? If a layout is properly efficiently done, you will have minimum area, minimum delay and minimum power. Okay, so how the length of the wires used, okay, and the positioning of the blocks or the positioning of the components, and if you have not properly placed the metal layers, there may be capacitance forming between the layers. Not only metal layers, between the layers there may be unnecessary parasitics, that is resistance, capacitance and inductance being formed, which will lead to again delay, okay, which will lead to more power consumption, and area also will be larger if you use more proper routing. If it is not done, okay, it can result in any of the it can result in deterioration of any of one of the parameter whichever I told you, area இல்லைன்னா power இல்லைன்னா delay, இது மூணுல ஏதாவது ஒன்று எஃபெக்ட் ஆகும். So proper layout, efficient layout வேணும், efficient routing வேணும்னா stick diagram போனீங்கன்னா it is one of the ways in which you can get benefited for obtaining a efficient layout. So now we'll see the color code that is used for drawing stick diagram for NMOS process. Okay, so in this table I have the color mentioned, stick encoding, and the layers, mask layout encoding. That is how do you represent the layout. uh, uh, Stick encoding is nothing but just color sticks. Layout encoding use rectangular blocks. And CAF layer, CAF அப்படின்னா Caltech intermediate form. It is nothing, almost like a code language. These the letters which have been mentioned in the screen shows. Okay, if ND is mentioned, it has to do with the shape shown in the table and the layer specified. Okay, so if ND அப்படின்னா உங்களோட rectangular block with end diffusion area in the color. So உங்களோட specification ஒரு 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 சர்க்யூட், ஒரு ஐசியை வந்து நீங்க ரீட் பண்ணணும் with help of code அப்படின்னா, this is just like a file format to read those 2D shapes. Okay, now you can see the color and the encodings. So we'll see green color stick will indicate n diffusion or n plus active. So in case of ஒரு normal MOSFET எடுத்துக்கிட்டீங்கன்னா 4 terminals இருக்கு: source, drain, substrate or body, gate. நீங்க அங்க எப்படி நீங்க source, drain, substrate, body ன்னு சொல்றீங்களோ, இங்க மென்ஷன் பண்ற நேம்ஸ் வந்து டிஃபரெண்டா இருக்கும். ஒரு source and drain எப்படி ஃபார்ம் பண்றோம்? You are performing diffusion of n plus area இல்லையா, n plus doping வந்து diffuse பண்றீங்க நீங்க. So here source and drain will be indicated by n diffusion or n plus active area அல்ல diffusion னு சொல்லுவோம். So the layer which indicates the source and drain will be n diffusion or n plus active. Okay, so likewise gate is nothing but the material used for gate, polysilicon, conventional material polysilicon. So gate is represented by polysilicon and metal for wire just like wires. Here metal 1 is used. You have more metals, metal 1, metal 2, நிறைய metals இருக்கு. Conventionally metal 1 is preferred, so metal 1 I am using. You have specific functions for various other metals. And contact cuts. Okay, so green line or green stick will represent a n diffusion, or green stick will represent a n plus source and drain terminal or drain area. Okay, so red will represent gate, polysilicon, and metal will be represented by blue stick. Okay, any electrical connection or any node that represents electrical connection will be represented by a black dot. Okay, you can see this column which represents the layout. That is stick diagram வரையறதுக்கு என்ன கலர் ஸ்டிக்ஸ் அது பார்த்தாச்சு. அதே மாதிரி லேஅவுட்ல நீங்க எப்படி அதை வந்து ரெப்ரசென்ட் பண்ணணும். Layout will be represented using rectangular blocks, just color rectangular blocks, or using monochrome coding or color hatching. Design யூஸ் பண்ணியும் நீங்க represent பண்ணலாம், இல்லனா வெறும் கலர் யூஸ் பண்ணி represent பண்ணலாம். You can use both color coding, color hatching as well as the block representation. Anything is okay, fine. So the same color using rectangular blocks it is defined. For contact cuts, a circle, black dot will go for stick diagram, and a square, black color square will go for layout representation. So for stick encoding, just color stick lines, and for mask layout encoding, it is rectangular blocks. As I told you, CAF is nothing but set of graphic primitives for describing the 2D shapes on different layers of a. So followed by again some more color coding mentioned for NMOS process. So here I have in the first column I have implant. Okay, NMOS implant, and then buried contact by a brown dot. In case of layout, it is a brown color square. Within that you have a cross mark. Okay, so implant will be used in depletion mode transistor. Implant எங்க யூஸ் பண்ணுவோம் அப்படின்னா, எந்த இடத்துல நீங்க வந்து அந்த டைப் ஆஃப் டோப்பிங் நீங்க கொடுக்குறீங்களோ, you will be, that is layer. So here it is NMOS process. Okay, so here you can take it as a n type doping. Wherever you have a channel or you have a area where already n type doping is done, that can be specified by n implant. Okay, so very important, the following these two rows describes how a transistor is represented in stick as well as layout. So whenever poly or gate crosses diffusion, okay, whenever poly crosses diffusion, then it is a transistor. Fine. Whenever a poly crosses the diffusion, then it is a transistor. Okay. So this is N-type enhancement mode. Okay. Normally what you learn, that is enhancement mode transistor. You don't have channel, you create the channel. Okay. N-type depletion mode transistor na already channel irukku. Okay. So anga fabricate பண்ணும்போதே N-type channel between source and drain it is available. Okay. So that area has to be mentioned. Okay. It has to be showed in stick diagram. That is why here you use a square, yellow color square. So yellow color square will represent implant. Okay, so you can see the layout representation. So color blocks with color hatching is used. One thing you must note, in case of stick diagram, crossing of gate or poly and this diffusion will give a transistor. This can be horizontal or vertical. Okay, so crossing will give me a transistor. It need not be a poly has to be vertical, poly has to be horizontal. I don't have any such rules, but layout la always poly will be vertical. Okay, so again here also crossing of poly in vertical and horizontal of your N diffusion will be giving a NMOS transistor. Depletion type abdina I have to mention the already available channel, so I'm indicating that via yellow color square which shows the implant. Color code for CMOS process. So NMOS க்கும் CMOS க்கும் ஒரு சிலது அப்படியே similar இருக்கும் color coding. Okay, so whatever is similar that you're seeing in the screen now. So N diffusion, N plus active, okay, polysilicon, metal one, contacted, over glass, இது எல்லாமே அதே coding தான். Okay, stick same green color stick will be used for representing N diffusion, red color stick will be used for representing polysilicon, blue color stick will be used for representing a metal one, and contact cut same as a black dot. Similarly for mask, that is layout, okay, block with color hatching or without color hatching for the same color அதே தான் யூஸ் பண்ண போறீங்க. அப்ப என்ன டிஃபரெண்டா இருக்கும்? Once you say CMOS process, both NMOS and PMOS come into picture. Yes, so right from your first unit when you learn switch level modeling, you designed basic logic gates for switch level modeling. NAND, NOR, idellame pathinga, they have been designed using CMOS basic CMOS static logic. So CMOS logic abdinale you will have NMOS and PMOS come into picture. So here I have already mentioned how to represent NMOS and all those. So what will be extra in this? How to represent a PMOS, and regarding that என்ன வருதோ அதெல்லாம் எப்படி ரெப்ரசன்ட் பண்றது. So now you can see P diffusion. So எப்படி N diffusion na N plus source and drain. So அதே மாதிரி PMOS க்கு P plus source and drain, P diffusion. P diffusion will be represented with the yellow color stick with green outline. Yellow color stick with green outline. Okay, and similarly blocked for your rectangular blocks for your layout. Okay, so P plus mask will be used. Why P plus mask will be used? Wherever you do P plus mask எங்க நீங்க யூஸ் பண்ணுவீங்க அப்படின்னா, எங்கெல்லாம் P type doping நீங்க பண்றீங்களோ அங்கெல்லாம் P plus mask யூஸ் பண்ணணும். ஓகே, CMOS ப்ராசஸ்ல லேஅவுட் நீங்க வரையும் போது wherever there is a P type doping, you must include a P plus mask over there. Okay, and dark blue or purple metal 2. Metal 2, it's actually violet color. It is not seen properly here. Okay, it is violet. And black dot for via, and this can be used for layout. Okay, so via அப்படின்றது என்னன்னா between two layers, if you want to connect two adjacent layers or two or more adjacent layers, நிறைய metal layers இருக்கும். So depending upon the necessity, if I want to connect between two or more layers, then I can go for via. So that is nothing but black dot again. Okay, and this one is very important. Brown dotted lines will represent my demarcation line. Demarcation line na என்னன்னா உங்களோட NMOS ஐயும் PMOS ஐயும் செப்பரேட் பண்ணும். That is, in any CMOS circuit you have pull up network and pull down network. Pull up network அப்படின்னா PMOS, pull down network na NMOS network. Okay, so all my PMOS and all my NMOS, okay, has to be isolated properly. Okay, my N diffusion layer and P diffusion layer should not overlap. Okay, my N diffusion layer and P diffusion layer has to be isolated perfectly. அதுக்கு நான் என்ன பண்ணணும், I will draw a demarcation line above which I will place all my P diffusion, below which I will place all my N diffusion. In simple terms, above demarcation line all P mass, below demarcation line all N mass. Above demarcation line pull up network, below demarcation line pull down network. Stick diagram la isolation க்கு demarcation line. இதே layout ல எப்படி பண்ண போறோம்? You have seen in the CMOS fabrication. You can go for two techniques, P well as well as N well. Okay, so P well அப்படின்னா என்ன, ஒரு N type substrate எடுத்துக்குவீங்க, அதுல P well வந்து fabricate பண்றோம். P well குள்ள N mass-உம் N type substrate குள்ள P mass-உம் fabricate பண்றீங்க. So in this manner you isolate N mass and P mass. Okay, likewise N well na enna pandringa, in a P type substrate you form a N well. Okay, so inside N well I will be fabricating P mass, inside P type substrate I'll be fabricating a N mass. So in this manner I will separate N mass and P mass properly. Okay, so in case of stick diagram, demarcation line. In case of layout, I need to specify N mass within the P well. உங்களோட total pull down network, total N mass, N diffusion area, அதோட connections, அது எல்லாமே வந்து you must be covering it with the P well box. Brown color rectangular box. Okay, and you must be clear in this. Yellow color rectangular block will indicate P plus mask. Yellow color square block will determine my implant. Okay, so now you can see the last one, global power supply connections or your ground connections, anything that is global line. Okay, that is indicated by a cross mark. Okay, VDD and supply, that can be indicated, that can be drawn as a cross mark. இதே layoutல பாத்தீங்கன்னா this kind of structure has to be followed. Okay, உங்களோட metal VDD and ground lines are nothing but metal one. Okay, so that metal lines, in that you have to form a contact in this way. Okay, this black square surrounded by a region. So இது எவ்வளோ இருக்கணும், என்ன width and length, all it has to be followed. It is in design rules. And why there is a yellow color square here in CMOS process. Okay, so I told you wherever P type doping is done, you have to mention with the square, yellow color square. Okay, so VSS ன்றது உங்களுக்கு வந்து NMOS-ல ground connection நீங்க கொடுப்பீங்க. Okay, substrate connection தான் இது. NMOS உடைய substrate வந்து P type. Okay, so அதனால இங்க வந்து P plus mask வந்து யூஸ் பண்றோம். NMOS உடைய substrate தான் வந்து ground கொடுக்கிறோம். So that is VSS substrate. Okay, so NMOS உடைய substrate என்ன type, P type. So அதனால இந்த இடத்துல வந்து you're using a yellow color square. Okay, most important. So same as your NMOS process, CMOS process also denotes crossing of N diffusion and poly as an NMOS transistor. Okay, same as your NMOS, here also I'm using. So but and this is also having a crossing of diffusion and poly. P diffusion is represented by yellow stick with a green outline. Okay, so here in case of layout, the same representation of NMOS is used, but you have to cover it with a P plus mask to show that P type doping is done over there. Okay, what are the steps to be followed? With the help of suppose I'm giving you a Boolean logic, with the help of the circuit diagram, CMOS circuit diagram, I must see the circuit diagram depending upon the connections and the transistors, number of transistors I have to follow. First I must draw the supply line and ground line, VDD and ground, and they are nothing but metal one lines, and I must leave enough space between the VDD and ground. Okay, in between VDD and ground I must draw the circuit, and then demarcation line to separate PMOS and NMOS network, and consider the number of inputs, or which determines number of transistors. So depending upon the number of transistors and the number of inputs, you go for drawing your N diffusion and P diffusion. and draw the and complete the connection. Okay, so your uh, stick diagram will be done. Okay, so some of the rules to be followed. So when two or more sticks of the same type, அதாவது ஒரே டைப் ஒரே லேயர், மெட்டல்னா ரெண்டு மெட்டல், பாலினா ரெண்டு பாலி கிராஸ் பண்ணுச்சு அப்படின்னா then their electrical contact is established. Okay, it means that there is electrical connection between these two. Okay, uh, when two or more sticks of different layers, different type, okay, that is poly or diffusion. Here it is poly and metal. Okay, அதே மாதிரி இந்த மாதிரி இருந்தது two different layers-னா then there is no electrical contact. If you want an electrical contact, mark electrical contact as dot. Just use stick encoding to establish electrical connection over there. Okay, ரெண்டு ஒன்னா இருந்தது, ஒரே டைப் ஆஃப் லேயர் ரெண்டு கிராஸ் ஆச்சு அப்படின்னா எலக்ட்ரிக்கல் கனெக்ஷன் உண்டு. டிஃப்ரெண்ட் டைப்ஸ் கிராஸ் ஆச்சுன்னா நீங்க மென்ஷன் பண்ணாத வரைக்கும் இட் இஸ் அன்கனெக்டட். just crossing of two lines, அவ்வளவுதான். Only if you mention a dot, then it is electrically connected. And your transistor, two different lines, poly and diffusion. Okay, so poly and diffusion cross பண்ணும்போது எந்த கனெக்ஷனும் நீங்க கொடுக்காம எலக்ட்ரிக்கல் கான்டாக்ட் நீங்க மென்ஷன் பண்ணாம இருந்தால்தான் அது டிரான்சிஸ்டர். ஓகேயா, if you mention a dot, then it is not a transistor. Naturally, when poly crosses diffusion, it is represented as a transistor. If it is mentioned, if electrical contact is established, represented as a dot, then it is not a transistor. Okay, and demarcation line rules. So your diffusion must not cross the demarcation line. N diffusion ஆகட்டும், P diffusion ஆகட்டும், it should not cross over the demarcation line. But your metal, உங்களோட poly இதெல்லாமே demarcation line மேல நீங்க வரையலாம். Now we'll be seeing how to draw the layout and stick diagram for a basic CMOS inverter. So this is my CMOS inverter. I have a PMOS, NMOS. The gates of PMOS and NMOS are tied together to the input. I have connected the source to supply. The drains are connected together to output. Source of NMOS to ground. This is my CMOS inverter. Okay. So as per the rules, steps we'll follow first to draw the supply rail, ground rail, and transistor. First I'm starting with the NMOS transistor. NMOS transistor na enna, N diffusion poly cross pananum, appada adu NMOS transistor. PMOS transistor na P diffusion poly cross pananum. So P diffusion and N diffusion. So N diffusion green stick, P diffusion yellow stick with green outline. Now poly has to cross. Okay, connect the drains of both your NMOS and PMOS. Okay, with the help of a metal. Take the output and input is given. Now VDD, ground. Okay, VDD and ground is represented as the cross mark. Now establish all your electrical connections. Wherever you need electrical connection to be established, எந்தெந்த நோட்ல electrical connection இருக்கணுமோ அங்கெல்லாம் black dot யூஸ் பண்ணி represent பண்ணுங்க. Okay, demarcation line. Demarcation line must be drawn at the beginning. Okay, so there is a mistake here. And input, your output, VDD, VSS or ground, demarcation line. So this is my stick diagram. And now I'm going to draw the layout. So stick diagram, once it is done, see the stick diagram, go for representation of layout. If you are if you know the CMOS circuit, transistor based circuit, you can easily draw the stick diagram. And once you are done with the stick diagram, you can view the stick diagram and parallelly represent your layout very easily. Similar to stick diagram, first I have drawn the VDD and ground. Again, hope you remember. In case of stick diagram, I can place polysilicon in vertical or horizontal mode. எப்படி வேணா நான் connect பண்ணலாம். If there is a cross between polysilicon and diffusion, then it is a transistor. அது poly வந்து horizontal இருக்கணும், vertical இருக்கணும், எப்படி எந்த directionல cross பண்ணாலும் அது transistor தான். but in case of layout, poly has to be in vertical. So I'm taking diffusion in horizontal here. Okay. So and likewise, again, in case of CMOS process color code, we have seen both NMOS and PMOS அதே greenல தான் represent பண்ணியிருந்தாங்க. But PMOS will be differentiated in by adding your P plus mask. Okay. So now crossing poly with diffusion. So two transistors PMOS, P plus mask is drawn. Now connect your source of PMOS to VDD, source of NMOS to DSS, both the drains to output. Okay. Place your pull down network or NMOS within the P well, brown color rectangular block. Contact cuts wherever there is interconnection, wherever there is electrical connection to be established, use a contact cut. Okay, and finally VDD supply. So this is my layout diagram, stick diagram and layout diagram. Now you can see the first diagram shows layout of again inverter. Okay, so where I have used color coding plus monochrome. Color hatching is also used. Shades use பண்ணி color blocks use பண்ணிருக்காங்க. Okay. And the next diagram shows here CMOS inverter design based upon lambda based design rule. Either in the mari scale use பண்ணலாம். If you know the lambda based design rule, you can sit back and check whether the rules regarding width, minimum space between the layers and overlap, okay, everything is being followed or not. Okay, either you can use this kind of scale or you can mention the minimum width and spacing nearby each and every layer, each and every block. Okay, so again here you have a P substrate contact. Okay, so I have not done this in the previous slide, so here I must do it for VSS. Why? I told you inside a P well we fabricate a NMOS. Okay, so அதோட body contact அதாவது அதோட substrate நீங்க வந்து ground பண்ணுவீங்க. Okay, so that substrate has to be indicated by P plus mask because it is of P type. Okay, you will, in case of NMOS, you will be connecting the source and substrate will be tied to the ground. Okay, so this is my CMOS NOR gate. This is my layout, sorry, stick diagram. So I told you already, if your stick diagram can be drawn in any way, that is when I draw the stick diagram it will be different, when someone else draws the stick diagram it will be different. In the mari neenga varayalam, provided the rules and the rules are being followed properly. Okay, the direction or the position of uh, 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 input. Okay, so input can be this side, input can be other side, எப்படி வேணா நீங்க வரையலாம். The connections and the color specification has to be correct. Okay, so that's all about your stick diagram and layout. So after knowing all this color coding and the rules, okay, design rules, you can practice for the following logic. Okay, you can take any boolean logic and you can practice. You can do it for an AND, XNOR, half adder. Thank you.